This video has to do with logs, introduction to logs, and what we want to do is look at how logs are the same thing as exponents. So we use this when the input, the variable, is in the exponent position, and we want to convert it into a form so we can work with it and solve it, just like we did between exponent and radical form. We can switch depending on the problem. Logs is another form to deal with exponents. So let's first identify the pieces of the log. So again, the objectives, we can see them up here, are: can we identify the parts of logs and exponents? Can we convert forms? And we're able to like simple evaluations of those logs. So let's take a look here. The three key parts are base, exponent, and result. So we realize in exponent we have a base portion and an exponent portion. That whole thing, a lot of times we referred to this before as the power. That power is equivalent to the result. So a lot of times those are the three pieces: the overall, the exponent, and what the base of the number is. So a log is the exact same thing, but we just rearrange those pieces. We put the base as a log. So every log is in terms of whatever base number. Base 2 numbers, base 3, so like 2 to the 4th power would be a base 2 number. So log base A of B. B is the result, and notice this whole thing is equivalent to what? An exponent. So a log is an exponent. So let's take a look at a quick example. So if I say 2 to the 4th power is equal to 16, I could put that in a log form and say log base 2 of 16. That's equivalent to an exponent of 4. So that is of the same thing. All right, let's take a look at some examples of conversion. So these are in log form. I'm going to put them in exponential form. So let's take a look here. So I'm going to start with identifying the base. I always want to start with the base. 5, and then the exponents over here to the 3rd power is equal to the result of 125. So I'm just looking at the positions: base, exponent, result. And when I read this, I would read this as log base 5 of 125 is equal to 3. Okay. Base 4, exponents on the other side, equal sign, is equal to a result of 1/16. Now notice what happens here. We have a negative exponent, which means we flip it, make it positive, and 4 squared is equivalent to 16 on the bottom. So again, we can see this with negative exponents and things of that nature. We saw this one on the example I just did on the other slide. So now here's an example where we have a variable. So we have a base of x raised to the 2nd power, and that should be equivalent to what? And what I'm looking at here is right here, x squared. That's the result, and notice they're identical. Okay, so where do we see? Now in all these examples, let me highlight the exponent piece. Here, 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 and here. And we could see it in the exponent form in the same position. Now what is equivalent to that? The log, right here. So let me rewrite, for instance, this one over here. I could simply say 2 to the log 232 is equal to 32. I could raise it to that power, and that power is what? Equivalent to 5. Okay. Take a look at this one. Now here's a great example: 3 to the negative 1 power. That means flip it, and to the 1st power, 1/3. Great example of showing negative exponents. Here's another one where we're showing how radicals play a part. So we have 16 raised to the negative 1/2. And that must be equivalent to a result of 1/4. So let's see what this looks like. Well, 1/2, make it positive, so we have 1 over 16 to the 1/2. 1/2 is the same thing as the square root. So square root of 16 is equal to 1 over 4. So there's a great example of showing negative exponents and radicals in the same problem. All right, now here we're going to talk about how can we evaluate logs. Think of them as exponents. So we're saying, okay, so this is equivalent to like an unknown. So I'm just going to put a big old box or a big old smiley face. I'm going to just put a big empty rectangle for all these. This is equivalent to what? So let's kind of rewrite this in that form. This is 4 to what power is equal to 64. So that's what that's reading. And you're going to look at and say, okay, what number goes in that place? Well, 4 to the 3rd power is equal to 64. So log base 4 of 64 must be equivalent to 3. So that is what we're looking for here. So let's take a look at this example. 2 to what power is equal to the result of 2 to the x power? See how the bases are the same and the equation is the same? So guess what? The exponents are the same. So that's equivalent to x. Here's another great example. 3 to what power is equal to 1 over 27. So the first thing I'm going to look for is, okay, how do we get it in the denominator? Well, it must be a negative exponent. And then how do we go from 3 to 27? We cube it. So 3 to the negative 3 power is 1 over 27. So this is equivalent to negative 1 or negative 3. So that's a great example over there. Here's an example. Now here's the one that's a little tougher because notice that we have a 3 and a 9. So this is 3 to what power is equal to 9 to the x power? Well, let's rewrite 9 to the x power. That's really 3 squared to the x power. And 3 to the 2x, I can combine those exponents and just put 3 to the 2x power. So now here's a nice thing. Now I did that, so now I have a common base. So what exponent is equivalent to 2x? 2x. Okay, so that's a great example of why we want to think of 9 in terms of base 3 numbers. Here's another one here where we have 1/2 raised to what power is equal to 4. So here's an example where we have a fraction and we need to put it into the numerator. So again, we got to bunk bed it, switch positions, and then square it. Go from 2 to 4, square it. Here's another one too. So right away, this is a lot like this problem here. We have from 3 to 9, went from 2 to 4. So I'm going to change 4 to 2 squared, and that's all raised to the x power. So really that's 2 to 2x. So now I have log base 2 of 2 to 2x. That whole thing is going to be 2x because it's saying 2 to what power is equal to 2 to the 2x power. Those two things have to be equivalent. Now here's a great example where we have 1. 5 to what power is equal to 1? Well, the only number that can go in that position that go to 1 is 0. So anything raised to 0 power is 1. So anytime you take log of any base and it of 1 will always equal 0 because anything raised to the 0 power is equal to 1. X to the 0 power is equal to 1. Anything. Now these last two examples, in fact, let's go skip 14. Let's go jump to 19 here. Anytime you do not see a base here, it's understood to be base 10. The reason why we don't write it is because we naturally work in base 10 numbers. Think about it. We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When we get to 10, we move a digit over and we start over again. 11, 12, 13, and get up to 19 and 20 and then start over again. So we work on base 10 numbers naturally. So this is 10 to the what power is equal to 10 to the 6 power? Well, this is going to be equivalent to 6. So anytime you don't see the base shown, it's understood to be base 10 numbers. Okay, so now we're going to put these exponents in log form. Okay, so I'll just go through all of them here. So we're going to have log and then identify the base, 7. Then you put the result, and again, it's always equivalent to the exponent. So it's going to look like that. So here we're going to have log of base 5, and the result is 1 over 25, and that's equal to the exponent of negative 2. This one, log, and the base is 1/9, so yes, we can have fraction in the base there, of 81 is equal to negative 2. Notice the use of reciprocals with the negative exponent. Log base 4 of 16 is equal to 2. So here's a great example of something, as you get better at this, you should be able to look at this and say, oh, that's 2. Because we were thinking about 4 to what power is equal to 16, that means it's a perfect square, so 2. When I see this one, I'm thinking, okay, reciprocal, so it's going to be negative, and 2 to the third power is equal to 8. So it's going to look like log of the 1/2 base of 8 is equal to negative 3. Okay? And the very last one over here, log base 5 of 125, saw this earlier, is equal to 3. So again, all I'm doing is I'm not really refiguring anything. I'm just looking at the positions and saying, okay, where does everything go? The base goes in the bottom. That might be a good way to look at it. Now it's nice and low. The result goes next, and I always look at the exponent as always the last thing. That's what's equivalent to. So again, in this video, we're supposed to pick up on what is a log, identifying the pieces, can we convert forms, and very basic evaluation of it.